Right, so we've talked about the first derivative test, which tells us about when we have a relative max or min, and so now we're going to talk about the second derivative test, which relates to concavity. So now we're going to talk about, now the first derivative kind of also will be part of that, and so we'll kind of see that. But if you have the first derivative and you have a function changes from increasing to decreasing or decreasing to increasing, we know there's a relative extreme up there. Well, same thing with concavity basically is that if some signs change in the second derivative, we'll have an inflection point, which means it changes from concave up or down. So we're going to have a very similar thing there. So here, and this is a really good way to get an example of what that means and how this ties into the second derivative. So if we were to draw little tangent lines at all of these points, okay, as we go around this curve. So this first curve is concave up, like a right side up bowl. Okay, so bowl turned the right way. What do you notice? So this is concave up. What do you notice about the tangent lines? Well, if you look, this one is negative. And then this one is a really small number positive. This is a much steeper line, so bigger positive, and then this is even bigger positive. So we can see that that means that the derivative, the slopes of those tangent lines are getting bigger as we go left to right. So we would know that f prime is increasing. Okay? If f prime is increasing, that means its derivative must be positive, which would mean the second derivative. That's how that's going to tie together. So same thing here. If we have tangent lines along this graph, and this graph is concave down, again like an upside down bowl. If it's concave down, we have a small positive slope, but then now we have a negative slope, and then we have more negative and more negative, which is smaller, right? So like if say this one was -0.5, this one might be -3, so it's getting smaller. So we know that f prime is decreasing. And we know if a function is decreasing, then its derivative would have to be negative there. Well, the derivative of f prime is f double prime, so that's why f double prime will be the way that we can determine this. But there's actually two different things that we can say. Both of these can be an explanation for whether something is concave up or down. And so this is important to know that there's two different things to say. So first of all, of course, we have to have our condition. So f has to be differentiable. Then the graph of f is concave up if f prime is increasing on the interval. And it is concave down if f prime is decreasing. Okay, and that again should make sense looking back at those pictures, the way the tangent lines would go. The way we test for it then, again, if f prime is increasing, then that would mean that its derivative, which would be f double prime, is greater than 0. So therefore, the test for concavity is if f double prime is greater than 0, then the graph of f is concave up. And then same thing would go for decreasing. If f prime is decreasing, then its derivative, f double prime, would be less than 0 or negative, then the graph would be concave down. Okay? So that's how we're going to test for concavity. All right. So we want to take the graph f of x equals 1/3 x cubed minus x, and we want to determine the open intervals where we have the graph is concave up or concave down. So to do the test for the second derivative, we're going to do f double prime. So first we'll find f prime, which is going to be 3 times 1/3, so that's 1, so x squared minus 1. And then we need f double prime this time, which is 2x. Now, we want to find out where the sign changes. Well, guess what? That's going to be the same type of thing we do with the first derivative. We want to find the places where it's 0 or undefined, and those would be the places that we would look. Now, instead of critical points, this is really, really important. These are not critical points. When I find that 2x equals 0, I find x equals 0. This is called a possible point of inflection. Kind of like when you find a critical number, those are possible places that we have a relative max or min. The way we determine if they in fact are max and mins is we have to test to see if the function changes from increasing to decreasing or vice versa. Same thing's true with the second derivative test, or the second derivative, the test for concavity. The place that the second derivative is 0 or undefined is a possible place that we have a point of inflection. So that's important to understand. This is a possible point of inflection, okay? So we would make the same sign charts, and I'm not going to use this little guy, but we're going to just make the same type of sign chart except with f double prime. So just like always, up here, write down what you're answering, f double prime. 0 was the only place, that's where the second derivative, which is up here, second derivative equals 0. So the only way that the function can change the second derivative from positive to negative is if it goes through 0, or there's a place that's undefined. And in this case, we didn't have undefined. So we just test it just like we did with the first derivative. So if I pick a number less than 0, and I plug it into this second derivative, so for example, we'll just plug in -1. Well, we're clearly going to get negative. That means that, and then let's go ahead and pick positive numbers. So obviously if I put bigger than 0, I'm going to get positive. So that means that f, okay, so this is what it tells me about f. F is concave down here and concave up here, which now also means that this point is a point of inflection, which we can abbreviate POI if you want, or you can write point of inflection if you think you're going to get confused. Okay, so we're going to answer, they only asked for concave up and down, but I wanted to go ahead and show you that because it changed from concave down to concave up, then we can say that that point is going to be a point of inflection. Okay, so then to answer the question, just like always, we need to give a description. So we would say f of x is concave up on 0 to infinity, because that's the right side there. And the reason is because f double prime is less than or greater than, we're on concave up, greater than 0. And that's what we put in the table, right? We found that f double prime was positive, so that means f is concave up. F of x is concave down on the interval -infinity to 0. And again, the reason we decided it was concave down is because f double prime is less than 0. Now, it didn't ask for a point of inflection, but if it did, we would say that there's a point of inflection at x equals 0 because f double prime changes from negative to positive there. Okay, so that's a point of inflection. All right, so let's go to look at this graph and its derivative and kind of look at how that summary goes. All right, so see how they're related to the slope. So if we have the graph 1/3 x cubed minus x, and we just put a few points on our graph here. So we would have at -1 and 1, we would have, because if you take the derivative, you get x squared minus 1. So that means 1 and -1 would have max and min points. And then we know that, of course, if we plug in 1 or 0, you're going to get 0 for this graph if we plug 0 in for x. And then it doesn't really matter what value we have here, but we do know that we're going to change from increasing, decreasing, and so on. So let's look at what that tells us by looking at the derivative. Okay, so we're going to use this sign chart here. So we know that the derivative equals 0 at 1 or negative 1 and 1. So if we look at f prime, so we're looking again over here, we're looking at that derivative, that function. If we pick a number less than negative 1, like negative 2, we're going to get positive here. And if we pick a number between negative 1 and 1, like 0, 0 minus 1, negative. If you pick bigger than 1, you're going to get positive. So that means that this function f, okay, f of x, if I try to sketch it here, it means it's telling me that it is increasing until it gets to negative 1, and then decreasing, and we know it goes through 0 because we know an easy point, and then it's got to be changing and it's increasing here. Now, I've drawn the concavity kind of in that part, but let's talk about the concavity when we see how it matches up. So if we look at f double prime, okay, so if we look at the derivative of this, f double prime is going to equal just 2x. So we're going to have just our 0 here. We just did this. This is the one we just did. So we know it's concave down, and we know it's concave up around 0. So let's look at the graph that I drew, and we're going to spend a whole bunch of time on that, on sketching graphs, but it's just so you can kind of see that. So you can see that the way that makes logical sense, it's concave down until I get to 0, and then I kind of have to turn and do concave up here for the rest of the way. And so that's exactly what fits this graph. Now we'll do a whole section on graphing and matching that together, but that's just giving you a little bit of that. Okay, so the definition, the formal definition of a point of inflection is that we have a function that's continuous, and we call it a point of inflection if the concavity changes from upward to downward or downward to upward. So either way. So the concavity changes, we have a point of inflection. Then this is important. Just if you have a point of inflection, then either f double prime is 0 or f double prime was undefined. Sort of like when we had relative max and mins. If you know there's a relative max there, then you know that the first derivative is either 0 or undefined. It's not true the other way around. Okay, so the second derivative being 0 or undefined means we have possibly got a point of inflection, but we have to check to see if the concavity changes. So we're going to actually skip a little bit of this, and we're going to look at the some examples. So, and a couple of things that we do make, it's possible points of inflection. I don't want you to call them critical values of f prime, because when they ask you for critical values are first derivative 0 or undefined, and that's it. So you really just list possible points of inflection is safer, because if you use critical values, you're going to think both of them are those, and that's not it. When you're asked for critical points, it's the first derivative, 0 or undefined. Concavity can change at a discontinuity, but then there can't be an inflection point. So remember how we do our sign charts, and we'll write undefined at the top, and then we have to be careful to make sure that the graph has that. And so where we would see that is this example that we kind of skipped over. But if you look at this graph right here, you have concave up, and then you also have concave up on both sides. So when we look at the derivative of it, you would have an undefined place for the derivative there at P, but it wouldn't be a point of inflection because you're going to get no concavity changing. Okay, so we're not going to have that. So I guess we can look at these. I just didn't want to do the ones above it, but these are good to look at. So for example, there's an inflection point right here at P, because this is clearly concave down and then switches to being concave up. Okay, so that's an inflection point. Here, We have concave up, and we do change to concave down, so it is a point of inflection. The thing that's different is the derivative would not exist. So that's why we have to check for the derivative not existing. So both of these have an inflection point. Here the derivative f double prime at p would be 0, and here f double prime at p is undefined. Okay, so, and that's the difference. So it just means that the second derivative is undefined. And then here's a place where we don't have an inflection point because concavity does not change. And here concavity changes. It's concave up here, concave down on this side. But obviously P is not a point of inflection because it's an asymptote. So we don't have that. Okay, so let's do some changes here to figure out if we have, on example 3, if we have points of inflection and talk about the concavity. So we're not going to actually talk about the first derivative. We're going to find the first derivative to get to the second derivative, but we don't need anything. It did not ask us about relative max or mins. So I need to find the first derivative, but I only need to find it in order to get me to the second derivative. So the second derivative, which I would normally do this right underneath it because I didn't need the first derivative equal to 0 in this case. Now sometimes you do, but here we don't. So, because they only asked about concavity, so I have 12x squared minus 24x. Now, of course, we can use when the first derivative is increasing, decreasing, but that's what we're going to get here. All right, so don't call those critical numbers, okay, and don't do this. So really just this whole chart, we'll just take this off. I don't want to do it that way. So you can sort of just ignore that on your paper. All we're going to do is make a sign chart. So you can even just do it. We can just do the work right here under f double prime and then answer the things on the right. So for f double prime, we need to know when is it 0 or undefined. Obviously, it's not going to be undefined. So we're going to find when it equals 0. So I'm just factoring as I'm setting it equal to 0. Remember how important that step is in order for you to communicate to somebody that you're solving that equal to 0. And then there are my 2 points. So I'm just going to make my sign chart, and I just need 0 and 2 on it, and I need f double prime. I'm going to put 0 up here because we know that's where f double prime equals 0. And then I'm going to pick a point somewhere in the range, and I'm going to check the second derivative. Remember, factored form, much easier to check. So if I pick, say, -1, which is less than 0, I'll have -1 times 12, so that's negative. -1 minus 2 is also negative, so I'm going to get negative times negative, which is positive. Then I'm going to go between 0 and 2, so like pick 1. So I'm going to get positive times negative, so that's going to be negative. If I plug in a number bigger than 2, I'm going to get positive times positive, which is positive. Which means that f is concave up, concave down, concave up. Now, if you want, you can draw concave up like this instead of writing the words, and concave down, because remember, this isn't justification anyway. This is just for you. But don't confuse that with increasing, decreasing, anything like that. That's why I always have you write those words. So, but concave up and down does help if you draw that. So you can certainly just draw that instead of the words. So the question is about concavity and points of inflection, determining the points of inflection. So here, because the graph changed from concave up to concave down, we have a point of inflection right there. And then it changed from concave down to concave up, so we got another point of inflection. Now, normally, when you give a point of inflection, it's called a point of inflection, so we're going to answer it as a point. So somewhere, and you can do this on the upper right where we crossed off that chart or whatever, I'm going to, I'll just do it right next to it. I need to actually plug in and find the points. So my original function, let me write it again so you can see it, x to the fourth minus 4x cubed. So I need to actually find out what is f of 0, luckily that's 0, and what is f of 2. So that's going to be 16 minus 4 times 8, which is going to be negative 16. Okay, so my points of inflection are the point 0, 0 and the point 2, negative 16. And that is the difference in how we answer them because they are called points of inflection. So in answering the question, points of inflection at 0, 0, and 2, 16. You could also write the points, you could write them this way, f of 0 equals 0 and f of 2 equals 16. It doesn't matter which way you write them, just give points or give that. And then we would answer when it is at concave down. Remember, all of these things are to tell what f is doing. We used f double prime to answer what f is doing. So ultimately, we're saying f is, which is again why we write right here, we write f. That's important so you remember that's what we learned. We learned about f. So f is concave up on the intervals minus infinity to 0, union 2 to infinity. Because we're always giving the reason. Oh, and we should give the reason about the points of inflection. So it's because f double prime greater than 0. And then we actually should have answered up here on points of inflection, so I'm going to add that. We need to say why those are the points of inflection, and that's because f double prime changes signs here. Okay, so that's why those are the points of inflection, or the concavity changes there. If we're listing the concavity, I would probably have listed the concavity first and then said, so those are points of inflection because the concavity changes there. And then we would say f of x is concave down on the interval, so that would be on 0 to 2. And again, our reason is because f double prime is less than 0. Okay, so really important that you give a reason every time, and really important that you really stress to yourself what's the difference in the test that we're doing. Okay, so we're going to do this example, and then we're going to look at something about how we can also use the second derivative to determine whether we have extrema. Okay, so we've already used this example before, 1/2 x plus sine x. We used it to find relative max and mins. Now we're going to use it to talk about where we have inflection points, point or points, and where we have concave up or down. Okay, so finding the first derivative. So this was an example we've already done. It was 1/2. Or I guess it was similar. I think it might have been 1/2 x minus. So anyway, this is 1/2 x plus cosine x. And then we find the second derivative. I don't really need the first derivative for anything because it didn't ask me about increasing, decreasing. So the second derivative is minus sine x. So again, we want to set the second derivative equal to 0. And give the answers. We've got to remember the answers are from 0 to 2 pi. So sine of x equals 0 lots of places. We only want the answer that is relevant here. So the only time that you're going to have, the times that you're going to have sine of x equal to 0 would be at 0, pi, and 2 pi on this interval. Now, because 0 and 2 pi are the ends, we don't really need to consider those so much, but I would draw them. We've talked about that too. If you do have an interval, it's good to go ahead and put those values on there. And then I'm going to have pi here in the middle. And then we again we're asking questions about or answering about G double prime. So we know G double prime was 0 here. And G double prime, if I pick a number between 0 and pi, and remember what I'm doing, I'm trying to answer what sign, S-I-G-N, do I get if I pick something from 0 to pi. Well, think about that. That's the top half of the unit circle. Sign will be positive there, all the way from 0 to pi. But then I got a negative sign out front, so that makes this negative. If I'm from pi to 2 pi, again, where the unit circle helps, that's the whole bottom of the circle. So sign would be negative on the bottom, but then it has a minus sign in front, so it's positive. So we would have, again, answer this question for G. G would be concave down here, concave up there. Okay? And so then we want to answer our questions. Since it changed from concave down to concave up, this is also a point of inflection, as long as it's defined in the original function. So to answer our question, we would say there is a point of inflection and it would be pi comma something. So we need to plug it in. So we plug in and do G of pi. I'm going to just do it up here. So G of pi would be pi over 2 plus sine of pi, which would be 0. So it's going to be pi over 2. So that's our point. And then we give our reason, because G double prime of x changes from negative to positive. Okay, so there's my reason that it is in fact a point of inflection, because remember, it was just possibly a point of inflection. The concavity had to change for it to work. Then I want to say G of x is concave down on the interval from, let's go back and look, and it was 0 to pi there. 0 to pi, remember not including the ends because they said open intervals. And then our reason for that is since, or because, f double prime is less than 0. That's what tells us concave down. And then concave up on pi to 2 pi. Make sure you don't say to infinity because we have a stopping point there. And that reason would be, of course, since f double prime, or actually g, I'm sorry, I wrote f on both of these. The function was called g, and be careful about that, because if you write the wrong letter, then you said something else. Okay, so the other thing I want to look at just briefly on this video, and then we'll do the rest in class, is about when we have the idea about what's called the second derivative test. So the second derivative test is to still determine whether we have, it's another way to determine whether you have a relative extrema anywhere. So if f double prime is positive, then we know that that means that f would be concave up. That's what we just learned. So let's think about it for a minute. If f double prime is positive, what does that mean about f prime? Well, f double prime is f prime's derivative. If its derivative is positive, then f prime must be increasing there. Okay? So that's kind of important in what is going to help us with using this second derivative test. So if f double prime is negative, then we know that f is concave down, and we know that f prime must be decreasing. Okay? If f double prime is neither, we have a possible point of inflection, but we don't know. We'd have to test it. And then if f double prime is not positive or negative, we can have a possible max or min here. Relative. Max or relative min. Okay? And the reason for that is pretty simple to think about. if you know that you have a part of your graph that's positive, so you know that that graph is concave up, and you know that the first derivative, so what we're going to do is, what if I knew the first derivative was 0 there? Was 0 in this interval at this point. So I know there's a point of, I know that the first derivative is 0. Well, that means that if this is concave up and the first derivative is 0, then that must be a relative minimum. If the function is concave down and the first derivative is 0, then you must have a relative max. And that's basically the first derivative or the second derivative test. Okay? Now, I'll talk about it more in class, but this is actually really, really important test, because if we know, because a lot of times on the AP test especially, because they want to know, do you understand the concept, you may not know any values of anything. The only thing they tell you is f double prime is negative and f prime is 0 there. Well, if f double prime is negative, that means it's concave down, and if you know that f prime is 0, then we know that we have a relative max there. Okay, so we'll talk about that in class. So we'll have more things to do. We'll probably spend a couple of days on this lesson, but that's it for this video.